Okay, let's do a review for exam one. Starting with real basic stuff. What kind of wave is sound? Think back to the first day of class, I think is probably when we talked about this, maybe the second day. But it's just and the easiest answer, looking for real basic stuff here. So what kind of wave is sound? It's a longitudinal wave. What about what is wavelength? Well, it's exactly what it says it is. It's like the length of a wave. It's the actual distance that's covered by a wave until it repeats. I think if you're not having trouble with this concept, great. Then fast forward this video by like 2 minutes. If you are having trouble with this concept that like there's a wave, there's length to it. Because usually you see it like, here's a wave. That's actually pretty good. So you usually see it like, here's a wave, and then we like follow along this wave. It's not moving, it's there. So it takes up a finite distance and we travel along the wave. But if you think about the fact that this is actually a sound pressure wave, and remember, an explosion or a volcanic eruption, the sound from that can travel around the world, and the sound travels from your computer to your ear. It's not really traveling from me to your ear now, but you know, if we're in person, then it does travel from my mouth to your ear. So it is traveling. And this representational sine wave that we have is kind of like moving out like this and to your ear. Obviously, it's in the form of a pressure wave and not like this exact depiction of a sine wave, but it's got sine wave characteristics to the sound pressure wave. But it does have a distance. And so essentially what you're measuring is, if you're thinking about a sound wave, you're measuring the compression to the next compression. So a compression front moves out, then there's rarefaction, then there's compression. And so you've got compression, rarefaction, compression. What is the distance from the beginning of the compression to the next compression? And there's a length to that, like an actual physical length. That's the length of the wave. Okay, what is period? The time it takes for a wave to repeat. This one, I don't think anybody has any trouble with. You know that there's a time related to a wave. And then what is frequency? Well, it's just the number of cycles in a given time. Hertz is cycles per second. So frequency is usually measured in hertz. It could be measured in kilohertz. Human range of hearing rate is 20 hertz, 20,000 hertz. Sometimes 20,000 hertz is 20 kilohertz. We'll just move up to kilohertz like that. And then I'm sure like if you look at, if you're into computers and stuff like that, you'll see like megahertz in terms of refresh rates for monitors and chipsets and stuff like that. So it's all cycles per given amount of time. Hertz ones are based in seconds. But there are others, beats per minute, all sorts of stuff like that. Frequency is just the number of cycles in a given amount of time. Frequency doesn't always have to be cycles per second. Hertz is cycles per second. And that's what we're using in our class is hertz. What's the relationship between wavelength and frequency? Longer wavelength, what frequency? It's an inverse relationship, which means if you have a longer wavelength, so a higher number in terms of wavelength, larger wavelength, then you have smaller number. Well, you have lower frequency, smaller number for frequency. So longer wavelength, lower frequency. Higher number for distance covered, lower number for cycles per second. 100 hertz wave has a longer wavelength than a 1,000 hertz wave, which would be shorter. And then what's the relationship between period and frequency? It's also inverse, similar kind of idea here. The longer it takes, the lower the frequency, so larger number for period, lower number for frequency. 100 hertz tone takes longer to repeat than a 1,000 hertz tone. Longer wavelength, lower frequency. Longer period, lower frequency. Why is this going to become important? Because longer tube, lower frequency. That's where we're going. We haven't really talked about this in class yet, and it doesn't really make sense to talk about in a review, but if you're studying this, you're going to hear me say longer tube, lower frequency in class after this. So longer tube, lower frequency. Essentially the same thing with wavelength. Longer wave, lower frequency. Okay, next. How are waves combined is what it says under my head. Additively. So this means two waves, if they sync up peak to peak, they're double as loud because it's just adding itself together. And if they sync up exactly out of phase, it cancels out. Nothing happens. If a 200, 400, and 600 hertz wave are combined, at what frequency does it repeat? That's 200. It's the lowest frequency in that group. What is the fundamental frequency? The lowest frequency of the grouping. Why is 200 hertz the lowest frequency? Why is it the fundamental frequency? Yeah, because it's the lowest, but also because those three frequencies, when they're grouped together, still repeat at a 200 hertz rate. So it's like the carrying frequency of the entire complex tone. No matter how many higher frequencies you put on there, assuming that they're harmonically related to 200, 200 is still the rate that they're going to repeat at. So it's still the fundamental frequency, and it's what you're going to hear. You're going to hear a 200 hertz tone. Okay, next. I didn't ask the question. What are harmonics? Integer multiples of the fundamental, which means 100 hertz is the fundamental. Multiply that by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you get 100 hertz, 200 hertz, 300 hertz, 400 hertz, 500 hertz, and so on. 200 hertz is your fundamental. 200 hertz, 400 hertz, 600 hertz, 800 hertz, 1,000 hertz, 1,200 hertz. Those are harmonics. Is every harmonic a resonant frequency? No, it's not. So don't make the mistake of equating harmonics to resonance. A lot of times it is a harmonic frequency that has resonance, but it's not every... So there's going to be more harmonics than there are resonant frequencies. Depending on where the resonant frequency exists for a tube, you may jump over 5 resonant frequencies before, or 5 harmonics before you get there. A resonant frequency may not land directly on top of harmonics. In fact, it might amplify like 2 harmonics partially because it's not quite right on top of them. Resonant frequencies are kind of harmonically related to one another. So I think that's where some of the confusion lies. But remember, harmonics are not resonant frequencies. They're similar to each other, but they're not the same thing. What is the fundamental period? It's the period of the fundamental frequency. So if you have multiple waves, like let's say it just tells you 200, 400, and 600. It says find the fundamental period of this complex tone. Well, you're going to see that one of those is the fundamental frequency, which is 200, and then you find the period of that fundamental frequency. That's the fundamental period of the whole thing. Doesn't matter how many harmonics are together. What does it mean to have a resonant frequency? It means that that frequency is amplified by the cavity, by whatever cavity it is. A tube or a cup or a bottle or a balloon, like whatever. A resonant frequency is the frequency that gets louder inside that cavity because the cavity matches the wavelength of the resonant frequency in some way. What else do resonant cavities do? Obviously, they resonate, they amplify, they also attenuate. So when something is resonating, that means that there's a frequency that's close to the resonant peak. It's going to get louder, made louder by the cavity, amplified by the cavity. When it's not close to the resonant frequency, it's going to be attenuated by the cavity. How many resonant frequencies does a mass spring model have? Just one. So if you're asked to figure out the resonant frequency for a mass spring model, there's just going to be one resonant frequency. We're going to change things, like we're going to change what the K is, we're going to change what the M is, and you're going to have to do things to the resonant frequency. But there's still just going to be one answer for a mass spring model. Just one resonant frequency. How about a Helmholtz resonator? How many resonant frequencies does a Helmholtz resonator have? Also just one. It's basically a mass spring model, like an acoustic version of a mass spring model. Try it while you're studying, but blow into... I don't have anything in here that's roughly bottle shaped. Nope. I don't think my coffee mug's gonna work because it's way too open. Yeah, no, it just didn't work. Is this gonna work? Well, anyway, you've done it, or you can. You'll get just like one frequency. Oh, there we go. There's like one frequency in there. You can almost... There it was. So there's like an actual frequency that you can hear. You can hum that frequency. Helmholtz resonator. It's a bad Helmholtz resonator, but it is. So pen cap works. Who knew? That's a resonant frequency. It's a Helmholtz resonator. It has just one resonant frequency. You can just hear the one almost sine wave sound to that. How many resonant frequencies does a tube have? Open at both ends. Many. We're only going to calculate 3, maybe 4. Like some of the slides that I have, we're looking at 4 of them. But I think you're ever only doing 3 on any of the exams. So pretty much just 3. That's all you're going to have to worry about. Does that change when it's closed at one end? No. It still has many resonant frequencies. What the resonant frequencies are might change. But the fact that it has many resonant frequencies is a constant. It's what happens with tubes. A tube open at 2 ends has how many pressure nodes for its lowest frequency? 2. Why didn't I make the 2 show up in the blank? Oh well, it doesn't matter. That would have been pretty cool. I don't know how it, maybe, probably couldn't figure, okay, it doesn't matter. So, just two pressure nodes for its lowest frequency. This is a tube open at two ends. I'm going to show you why this is in just a second, but let's go through the rest of these really quickly. If you get this, then again, you can fast forward through the explanation. If you don't, you should definitely watch the explanation that's coming. A tube closed at one end has how many pressure nodes for its lowest frequency? Uno. Just one. The lowest frequency a tube with two open ends can resonate, two open ends, is how many times the wavelength? It's 2 times the wavelength. You can fit half a wavelength in, which means you can go double. The lowest frequency a tube with one end closed can resonate is how many times the wavelength? 4. It can fit a quarter of a wave. So in any tube closed at one end, you can fit a quarter of the wavelength at the lowest. You can fit higher than that. You can fit more. But the lowest you can fit is a quarter of the wave, which then means the lowest frequency it can resonate is 4 times that length of tube. You get a wavelength, that's the length of the tube, but you only got a quarter of the wave in there. Multiply that by 4. That's the lowest wave that can be that can resonate in a tube closed at one end. Okay, if you get this, again, you can go through the next portion. If you're not understanding these, let's take a look at this really quickly. I need to make my head, what do I need to do here? I need to shrink myself. It's so small. Okay. Here you're looking at velocity and pressure at the same time. Usually I've only got like images of these to show you one. Here's both. Remember, I'm going to try to always give you velocity in green, which is why I had to kind of poorly draw over top of this. And they've got pressure in red, which is how you're always going to see pressure. So that's great. Okay, so let's draw your attention to a couple things. Number one, first thing is, oh, maybe we're looking at the wrong thing. Hang on, do I have these out of order? I do. Let's talk about this first. This is open at both ends. This is closed at one end, or open at one end. Whatever, it's the same thing. So open at two ends, open at one end. You can fit this half wave inside. You have to have an antinode, a velocity antinode. It's green, so we're looking at velocity. You have to have an antinode at both ends of a tube open at both ends. Pressure has to be at a node. Antinode just means it's not a node. Pressure has to be at a node at both ends because the tube is opening into the air. So of course there has to be a node. Remember, a node is not positive or negative. It's not a minimum. We talk about velocity maximum and pressure maximum. It's probably more effective to think of those as antinodes because the maximum is the minimum. It moves up and down. So here's our wave again. And if there we go. Kind of ignore the fact that I'm making this move with my right hand. Oh, let's move it over here so you can't see it. Okay, so the wave is moving up and down like about right here where my head is. It's a max and a min. Like at one point, like max, and then it's min, and sometimes it's right in the middle. But it can do all those things, right? It can be max and it can be min in that position. But right here, where this hand is holding it, it's never positive, it's never negative, it's always 0. That's a node. My hand right here with the watch on it, this is the node. The middle of the string is an antinode. And the other hand, pretend it's not there, because it's in a system that's actually making noise, this hand wouldn't be going crazy like this. So the antinode is the string right about here. The node is this hand. So when we say velocity max, when we say pressure max, what that means is also it can be min at any time, maximum and minimum. It's doing the same thing. It's oscillating in that zone. So the node, it's node and antinode. Probably a more effective way to talk about that. And remember, node just means 0. It just means that it's zeroed out. The air that's around me right now, the air that's around you right now, unless like you live in a vacuum, which sounds cool. But if you don't live in a vacuum, the air around you right now obviously has a pressure. That pressure fluctuates when there's storms. That pressure fluctuates if you have air condition or heating going at any time. But it doesn't really matter. It fluctuates a little. We zero it out. We just consider it when we're measuring frequency and pressure and velocity and all that stuff. We just consider the air around you, quiet air, 0. So there's 0 pressure. We change from baseline. It's baseline pressure. It's not 0 pressure, but it's baseline. So we have a node. At my mouth right here, when I say wah, it has to be a node where my mouth hits the air outside. I have an instrument that I made out of PVC pipe that I'll bring to class. There's a reason I have this. But same idea. It's a tube closed at one end. Here's the open end. At the closed end by my mouth, it doesn't open back out into the room. All that happens is I'm shooting air into it. So there's no reason why this needs to be a pressure node. It's not. It's a pressure maximum. But here at this end, it has to, it opens out into the room. So this end has to be a pressure node. Again, there's a reason why I have this. It has to do with like M's and N's, like nasals. We'll talk about it. So you can get like a horrible noise out of it. But I changed where the blockage is, and now this end is open to the room, and this end has to have a pressure node because it's hitting the air pressure out here. So in a tube open at both ends, which would be just this right here, this tube, which I can blow through. Both ends are open to the room. Both ends have to have a pressure node because the pressure that's here is the pressure of the room. So all that means is there has to be a pressure node in that position. Pressure and velocity are opposite one another, which means that there has to be, if there's a pressure node, a velocity antinode. And now I'm just going to point at you with this piece of plastic. So if there's a pressure node, there's a velocity antinode. That's what you're seeing on your screen right now, is right up here, 2 velocity antinodes. There has to be antinodes at both ends. Why is that? Bernoulli principle. We talked about that in class. But imagine you have, This is real dumb. I hope you just know why. But here's a reason why. If you imagine that you have a straw or this thing and you're shoving Play-Doh through it, and you can only have a consistent amount of pressure, just pushing with the same amount of pressure, and you want to get no, okay. You can have differential amounts of pressure because we have pressure max inside the tube and we have pressure nodes inside the tube. So you can push with more pressure inside the tube, but once you get here, you can't push with as much pressure to push all of the Play-Doh out. So if you can't push as hard, what is a way that you can clear all the Play-Doh out of the end of this at the same time? It has to go faster. Like it has to move through faster. You can push the same amount, but if it's moving faster, then it's moving the same speed as if you could push harder up here. So there can be more pressure or there can be more velocity. There's not going to be both at the same time. You're going to have a node and an antinode. Hopefully that makes more sense. Probably better than the 3-foot person inside of 6-foot pants or whatever. That one didn't. I don't think that worked. So this is going to be true for every frequency that can resonate inside of this tube. You need an antinode, a velocity antinode at both ends. You can put half a wave in. You can put an entire wave in. You can put a wave and a half, 2 waves, 2.5 waves, 3 waves. They can all fit inside of there. Totally fine. Because as long as there's an antinode, you can make it fit. On the other hand, closed at one end has to have a velocity antinode at the open end. So like I was saying, my mouth, if I'm, just like singing here, it has a velocity antinode. It has a pressure node at the open end at my lips because it goes out into the room. At the larynx, it does not open into the room. In fact, here it opens into my lungs, which are, when I'm speaking, always pushing air out. So it's not a pressure node, it's in fact a pressure maximum, which means it's a velocity node. So we have a node here, and we have an antinode here, which means the lowest you can possibly draw in there is this 1/4 of a wave. Look, it's just half of this. Here's that same shape. So it's just 1/4 of a wave. You can fit not half of a wave in here because it has to end up at an antinode over here. You can do 3/4 of a wave because it would come up, cross over, and end up down here. That's acceptable. You could do 1 1/4 waves, but not a half, not 1, not 1 1/2, not 2. So it's different. Okay, let's jump back to this. This is basically showing you why you can do 1/4 and then 1 1/4. So you started a node, you have an antinode. You started a node, you have an antinode. You can't do anything between. So you can do this, which just stops right here. And that works because you have this antinode. Nowhere else do you have an antinode until you get to 1 1/4 waves. And then same thing here, you can do 2 and this is 1 1/4. This is 3/4 of a wave. Sorry. Here's 1/4 of a wave. Here's 3/4 of a wave. This is 1 1/4 waves. And then this is pressure over here. This is just showing how they're opposite of one another. This is the same tube. See, the closed end is on the right side. Well, here the closed end is also on the right side. So it opens, velocity maximum at the open end, pressure node. pressure maximum at the closed end, velocity node. Okay. Here's some formulas that you're going to need to know for your exam. These are going to be on the exam for you to reference. You're going to see, essentially what you're going to see on the exam is the right-hand side, the white bars, and not the orange and yellow bars. So I'm not going to tell you what they're for, but I am going to tell you what the formulas are. You're going to have to know what they're for, but you'll be given the formulas. Frequency equals 1 over t, very easy. T equals 1 over frequency, also very easy. Mass spring, the only thing you're going to have to do with it is you're always going to be given the resonant frequency, and you're going to have to figure out how it changes. Helmholtz resonator, you'll have to figure out the whole thing. I'll give you AVL, and you have to figure that out. A tube open at two ends, you're going to have to figure out the first, second, and third resonant frequencies, and then the question is going to say, hey, the tube you just calculated closed. Now figure out, closed at one end. Now figure out the new resonant frequencies. Not too hard. Watch the math review if you need extra help with those. And remember to do the math practice sheet too. What does a spectrum of harmonics from the vocal folds look like? It is harmonics that gradually become quieter. Let me show you a picture of that right here. So this is the laryngeal source. Here's the harmonics. And you can see that they kind of gradually get a little bit quieter. We'll talk about why that is in the next, for the next exam. But for now, all you need to know is they're harmonics that gradually become quieter. How does the filter of the pharynx and oral cavity, why did I think that said how? What does the filter of the pharynx and oral cavity do to the sound from the vocal folds? It amplifies and attenuates harmonics from the source. So you get the above, you get those harmonics that gradually become quieter, and then the filter from the pharynx and oral cavity are going to amplify and attenuate those harmonics. This means the output into the air is a combination of the sound source and the filter. Again, here's that graph that I just showed you. Here's the laryngeal source, harmonics that gradually become quieter. Here's the filter. So here's where you've got a resonant peak. Things are going to be attenuated here. Things are going to be attenuated here. Resonant peak, so things are going to be amplified, attenuated. Another resonant peak, things are going to be amplified, and then things are going to be attenuated quite a bit over here. And the output is a combination of the laryngeal source and the filter. So the source and the filter. And you see basically the same shape here. You've got coming up, amplified, so attenuated over here, amplified, small attenuation, amplified, attenuated, and then amplified here. Attenuated, there's that bump right here. This is amplified, and then a lot of attenuation coming down. Next. I think this is our last slide. What maximum is at the open end of a tube? Probably a tube closed at one end. It's a max V. Velocity always at the open end of the tube. Pressure node, velocity maximum. Constriction at max V makes resonant frequency what? Lower. Cool. So let's throw some max V's and max P's on these. I need to move my head. Okay. Move the wrong thing. Whoa, man. There we go. All right. So what happens to resonant frequencies when there's a perturbation at the arrow? Here comes the arrow. Wait, before I drop the arrow. I've got green drawn on here, so this is velocity. You're always looking at velocity. max V is where we've got the most open end all the way to the top, right? So there's max V, max V, max V. Pressure maximum is going to be where there's a velocity node. So I could write it as velocity node, but I could also write it as max P, because the opposite of a max V is a max P. Pressure maximum is where there's a velocity node. Okay, so at the open end, there's always max V. There's always velocity maximum. So here's our arrow. What happens to our frequencies when there is a perturbation at this arrow? So we just answered this question. Constriction at max V makes resonant frequency lower. Constriction at max P then makes resonant frequency higher. So here, is this closer to max V or max P? It's closer to max P, which means frequency is going to get a little bit higher. It's not right on it, so I'm not going to say like large increase, but I'm definitely going to say increase. It's like solidly there, it's definitely an increase. That's for the first resonant frequency. The second resonant frequency gets a little sketchy. Here's max V, so frequency is going to get lower. Here's max P, frequency is going to get higher. I would say probably no change. Maybe now that I'm looking at it, it looks a little bit closer to max V, so you might get a slight decrease. The answer that I have written in the slide is no change. But now looking at it, I think it's probably slight decrease. And then what about third resonant frequency? It's right on the max V. Large decrease. Absolutely large decrease. But here's the answers. Resonant frequency 1, increase. Resonant frequency 2, no change. Resonant frequency 3, large decrease. And this is what I was telling you about on the exam. If you see these ones that are obvious, resonant frequency 1, increase. Resonant frequency 3, large decrease. You're not going to have an option that says no change, and then you're going to have the same two options over here and slight decrease. Like that's not a cool question to ask you, because it's really hard to gauge where exactly you are without like tick marks or numbers or something like that. So you're not going to have one that says, oh, slight increase, slight decrease, or no change, and that's the thing that your grade hinges on. No, not true. So if there's one where you can't tell, just kind of go with no change or slight, whatever. Go with the ones that are big, where you can definitely see that something's happening. Because what I would do is, the answer that you should not choose would say resonant frequency 1 increases, resonant frequency 2 no change or slight decrease, resonant frequency 3 large increase. You know that's wrong. That's how I'm going to put questions that you don't want to choose that as an answer. Okay, so look for the big things, not the little things. I'm not trying to trick you. I want you to get the obvious things right. And that's the last thing there is for this. So good luck. And yeah, good luck. Watch the math review. And then I'll see you for working towards the next exam.